curious, for starters, how many people are aware of Famfs? Not Paul, Alan, cool, nice. Good. So yeah, this is a different kind of a thing. So real quick, I'm John Groves. I'm a technical director at Micron. I am also co-chair of the Software and Systems Working Group at CXL. And I'm the primary developer of Famfs. Sort of the background on this is that, 2.5, 3 years ago, the imperative from my management chain was, we got to find the killer app for CXL, especially shared, because if you just online it as system RAM, that's just has to work, right? And I came to the conclusion, one, we needed an access method. Two, we needed to really figure out how to use it and show people how to use it. And then we would be able to look at good use cases. But Famfs is open source. This is really not a technical, or it's not a marketing thing at all. It's technical enablement. And so, all right, let's get moving here. So a quick level set. It's real important to think about this with shared memory or with CXL memory, disaggregated memory in general. There's two categories it falls into, system RAM and not system RAM, which surfaces as DAX. If it's DAX, you can do a makefs of Famfs on it, and then it's a file system. But if you online it as system RAM, sharing is nonsense, because it's going to get zeroed. Somebody else onlines it, they'll zero it too. Game over. When it's system RAM, there's a whole lot of interesting research being done about hotness detection, migrating to the right tier, things like that. This talk is not about that stuff. That stuff is interesting, and frankly, as a research area, I think it's a little crowded, because when you're moving pages around, you're making them unavailable for some period of time. So moving a cold page is free, basically, but moving a hot page is expensive. And so this is about how we make shareable, but also CXL memory that we're not giving to Linux. Linux can't hand out those pages or use them in the page cache or whatnot. And so, yeah, we're about to see the availability of disaggregated CXL appliances with switches in them that scale to like 100 terabytes by next year. And so that's really interesting. Of course, you can do two kinds of enablement with it. You can provision some, add it as system RAM for a host, and then just use it as system RAM. That's the not shareable case. The one that I think is interesting and is looking really promising is putting data sets in the shared memory and actually sharing them. And so what I'm going to go over here is a few slides about how not all problems fit in memory. It's an interesting thing, especially with AI, where there's a lot of people studying what people do with AI workloads. And the number of people who can tell you why they do that, why they don't do something else, is actually much smaller, because it's, we do things the way we do things. And so a lot of this, I think, a lot of my thinking around Famfs is how would we do stuff if we could, All right, so the not all problems fit in memory. A little bit about shared memory challenges, because we have them before we get disaggregated memory. And they're the same, they're a little worse now. What's it going to look like? I'm going to talk about DCDs, dynamic capacity devices, which is the thing that's going to be in the CXL memory clusters. It's basically a memory device with an allocator built in. And if we hadn't specified this in the CXL spec, I grant it's kind of confusing. I apologize for my role in that part. But we would have had to invent something to do those things. So good news, a lot of it's covered. And then I'm going to talk about Famfs, how it actually works architecturally. If there's interest, I'll delve into why files is the natural access method for memory. Because it turns out files are deeply embedded in the way you map virtual memory. So it was just kind of a natural thing to do. All right. And a quick slide about Famfs, just because if you don't know anything about it, some of this might not make that great a sense. But it's open source. Memory is accessible as files. If you memory map a Famfs file, you never have faults involving data movement. If you touch an address in a memory mapped Famfs file, a cache line loads. It's memory. If you do read and write, it's memcopy. And so basically, I'm going to talk about the limitations of Famfs. There are some significant ones in the sort of MVP level where we are today. But any app that can use data in files can use data from Famfs, within reason. We'll talk about those limitations. POSIX permissions apply. So you can now have file spaces full of actually in-memory objects and, owner group, other permissions, which turns out to be of interest to some of our partners. Okay, so not all problems fit in memory. Hey, Brian, I studied physics in the mid-'80s, and we used to say, not all problems fit in memory. There's two kinds, the kinds that do and the kinds that don't. And it's still true, except that memory is a lot bigger, and we've got more techniques now. And the techniques we've got, number one is demand paging. I can memory map a database that's way bigger than memory and perform queries against it. Also, via reads and writes, you can do the same thing. But I'm going to thrash it in and out. And so some workloads, if it doesn't fit in memory, you do that. The next one is scaling out. And if you scale out, generally speaking, you're going to have to shard. I'll stay with the database analogy for the moment. You have to shard up the data or the database. So if the problem shards well, great. And then we've got scaling up. How do we make memory bigger, more CPU, et cetera? And that only goes so far with x86 servers. This year, I think you can buy servers that can take 4 terabytes of DRAM per. Beyond that, you have to go to the other techniques. But with the shared memory, we're playing around with the phrase scale up and out, because the data sets, again, by sometime next year, we expect to be at 100 terabytes on current build technology. And so if you build a cluster that shares access to 100 terabytes of index or graph turns out to be a really good use case for this. If I scale out and access in it, then in some sense I'm deduplicating it too, because I don't have to have multiple copies, and I'm avoiding sharding, and so there's some real goodness there, particularly if there are problems that benefit heavily from being able to put something in memory that just doesn't fit in memory on anything right now. So, a quick cartoon of what it might look like. The Famfs files, any DAX device can be formatted as a Famfs file system. Famfs will soon span multiple DAX devices. It already interleaves across multiple memory devices, which I'm going to talk more about that a little later. But an interesting thing we've learned that, so see that picture of the VM connected to 32 terabytes of expansion memory. We were recently doing some benchmarking with 5 terabyte graph. And that's significant because graph analysis is one of those things that's really needs to fit in memory bounding on it. And we're working with a partner on graph analysis competency. But the first thing that happened was they told us how they would like us to generate a 5 terabyte graph with Graph 500, and Graph 500 fell over. And then the graph guys spent a week fixing it. but that's a data point that says, yeah, people aren't doing 5 terabyte graphs right now. And one of my colleagues likes to point out, except the NSA, I'm pretty sure they are. And they're building purpose-built big clusters. The other, actually I'm going to stay away from that for a second, but one of the things that it turns out is true is if you use the tool chain that we use for wrangling data, so you get data from somewhere, let's say it's CSV or it's scraped out of a log or something, but if I want to import, an amount of CSV that's going to be 5 terabytes of vectorized data in memory, I'm going to need a lot more memory than 5 terabytes, starting with the CSVs bigger than that probably. But, and those tools don't know how big the data is going to be when they start. So they allocate some memory. Think of pandas data frames, right? Allocate some memory, allocate some more. Something like 5x the size you're going to end up with, and maybe more, is kind of how much memory, working set memory you need for it to do this kind of thing. And it's pretty clear that and this isn't even a Famfs thing, but if I need to spin up, a 5 terabyte database, I might spin up a VM with 32 terabytes of system RAM. VMs can be backed by DAX devices as their memory. That's already in there. So fire up the VM with a lot of memory. It's not a particularly performance critical thing when I'm wrangling data to get it to the point where I'm going to do analysis on it. But then once I've done the thing that's really memory inefficient, I can give back that 32 terabytes of memory, just shut down the VM. The reason for the VM is because if it's bare metal, if you've given it memory as system RAM, it's either there when it boots or it comes in as a hot plug event for memory. But Linux can't necessarily give back system RAM. It often can, and sometimes can't. And there's not work underway to make that always work yet. But a VM is great because spin it up, give it enough memory from the big external pool. All right. So another thing we've learned is that the real superpower of memory, and this is semi-non-intuitive to me, the real superpower is low latency random access. And if I've got sequential stuff, I can stream it with NVMe. I can stream it from RDMA into the page cache. I can call madvise don't need on it, and those pages will get pretty aggressively freed. But if my workload is really random, and by random I mean non-prefetchable, now look at these latencies. So system RAM, unloaded, latency 100 nanoseconds. Switched, and this is a measured number, the disaggregated memory, I've got a 4-server cluster in the lab with 5.5 terabytes right now that we're playing with. And local socket latency to that memory is 450 nanoseconds. Remote socket is more like 550. But the important part isn't that that's 5 times as high as system RAM. It is, but if your stuff fits in system RAM, put it there if you care about performance. What's important is that, call it 500 nanoseconds, is 100x lower than the generally accepted best case unloaded latency of NVMe. Now, people are working on getting that latency down. If I move a page from NVMe, 4K, let's say, the data movement's less than a microsecond. So that 50 microseconds, that's not data movement time. That's reading the media. And if it's the optimal latency, which this is more or less, then we're not doing any heroic error correction. If we have to do heroic error correction, it's longer. But anyway, so for the disaggregated memory, it's for stuff that's too big to put in system RAM, or that it's not worth putting in system RAM. That's possible too. That I would otherwise either have to shard and then pay the penalties of following graph edges that send me to another shard, or demand page. And by the way, I'm happy to take questions as interruptions. All right, so, simple flow chart. Starting to seem like a marketing pitch, but again, it's open source. This is enablement. So say I got huge data. I mean, question number one is, can I do some kind of data reduction on it? There's a lot of problems where you can. If you can, great. I don't have data that's too big anymore. But if I can't do that, can I shard it? There's a whole category of problems that are known as the embarrassingly parallel data algorithms, whatever. And those shard really well. So there's just no downside to sharding, except it's complicated, but you've probably already got a Spark cluster or array cluster or something if you're considering doing these kinds of things. So if you can shard it, hey, great. If the axis is, next step, if the axis is sequential, now you can use RDMA, you can stage it, because that works really well. And the bandwidth is good. But if none of those things work, again, my example is graph, then disaggregated memory starts to make a lot of sense. There are also in-memory, indexes where you need in-memory performance, and sharding is hard to make work. So quick cartoon of use cases that we've identified. Graph analytics, kind of top of the list. RAG and LLM, especially graph RAG, which is starting to be a thing. Graphs tend to not be prefetchable, the access patterns. And so this looks good for that. And big data indexing. So there's a big ecosystem of tools and applications that use data frames. And if I'm going to put something in shared memory FAMFS files, it's probably data frames or something like that, where columns are vectorized, vector instructions work on them. And that's if I'm doing compute. And if it's graphs, that's a little different. But, but these are the kinds of things, these data frames that have already been put into an optimal format are ideally what you would put in there. And not your CSV that you're going to import, right? You really just have to scan through that once. It may be huge. Okay, so the challenges around shared memory are many. Actually, it's not that many, but they're problematic. And right now I'm talking about shared memory before we disaggregate it. So, you need to do some kind of synchronization. The tools that we have are atomics, barriers or fences, and locks, which are combinations of atomics and barriers and fences. And the really important point here is this stuff is already so expensive that we try not to do it. And when we're doing it inside one server, the CPU is actually never interacting with the memory directly. It's interacting with the cache. And if I call, so say I'm going to put a message into a queue, and then I'm going to update it. So it's like producer-consumer problem, computer science 201. Write the message to the queue, update an index so the message is discoverable. So I need to make sure that the message is readable by the time it's discoverable. So I have to write the message to the queue, write barrier or store fence, and then update the index. And then a fence after that's optional, you can do it. And then on the read side, when I discover that a message is in the queue, I read the index, discover it's there, load fence or read barrier. Now I can read the message in the queue, because there are things that the cache can be doing where if you didn't do that barrier, it thinks, I can let you see a stale cache line. Doesn't happen on Intel because they're strict global write ordering. Does happen on ARM power. Don't get me started about alpha, which I remember, but oh boy. Yeah, so, but the big thing is that we're already trying to avoid that stuff. And that's good, because it's worse with memory. I've got a slide or two on that, when the memory is actually disaggregated. But take Redis. With Redis, you don't scale up on one server as in having 64 Redis threads on a 64-core server. What you do is you have 64 Redis instances, and each one's single-threaded. And you use consistent hashing to figure out for a given key which instance does it get stored at. And so now Redis is lockless. And I'm sure it does a few things that are lock-up. It has more than one thread in each instance, but only one thread is doing either a put or a get. And so, this is where we already are in computer science. We're already trying to avoid locks. And so when it's shared, all right, I got to do a reset and see what I said here. Yeah, so first of all, configurations, and we'll come back to the synchronization. In CXL 2-ish, and by the way, it's speaking for the CXL consortium, we strongly discourage referring to a given device or switch or whatever as a CXL 3 thing or a CXL 2 thing, because there's just too many optional things in each. But in the future, we'll have DCDs. Memory can be allocated. A DCD, you can discover it. Actually, I got slides on this. I'm going to not go deep here on this now. You can discover it. You can program the decoders to access it. But you can't actually use any of the memory until you allocate some. And when you do, it can be shareable or not. It can be read-write or read-only. I actually put that in. And it can be hardware or software cache coherent. And cache coherent, we'll talk a little bit more about what that means, but it doesn't mean necessarily everything one would think. Yes? Hmm?
So you were talking about the lock, for the shared memory lock thing. Again, I'm not by any means knowledgeable on CXL, but my understanding is you can, if you are updating data or you are from one of the CPU or if you're updating data, you can inform that the data is getting updated, and because of the cache coherency, you already know whether the latest data is sitting in the memory or it has to refer back to the cache, and therefore the peer CPU, if it has to access the same address, it will have to wait for the coherent cache to become memory to become coherent before it can access. So it's CXL protocol built in that locking mechanism.
So yes, and it's more complicated than that. Oh yeah. So asking about whether one host updating memory knows when that memory is visible to other hosts, and whether a host waiting to access some memory that's being updated by somebody else, how they know. And the answer is, at the highest level, you already have to do it correctly if two processes or two threads are sharing a memory map file or a buffer that was allocated. You already have to do it correctly. And what you've got as your tools with actual local memory, you can use locks. The thing that CXL is missing, I don't think it's on the next slide, but is atomics. CXL does not supply atomics. Now, it does do this with the CPUs implementing it correctly, which they have so far to everything I know about. They do implement memory ordering correctly. So if you use your barriers correctly, then that works. And then if the memory is cache coherent, then then ideally each memory controller knows which cache lines are loaded on which hosts. Now you can do this without, and you can broadcast a back and validate every time somebody accesses a cache line. And good luck with that. It's not going to perform very well. But if you keep snoop filters, then anytime the second host that wants to read what the first host put there goes to access that cache line, a back and validate will be sent to the other host, which at the end of that, the cache line has been invalidated from that host, and if it was dirty, it got written back. But that doesn't get you all the way there. You still have to do things correctly, and my argument is that use cases that that look like publish and share turn out to make the most sense, because we're already avoiding fine-grained mutation of memory contents when it's just shared among threads. And it turns out a lot of our use cases already don't do it. So, and I think some more of your question will get answered in the next handful of slides. So, yeah, on CXL, barriers are supported, but atomics are not. That means that, this picture is a ring buffer or producer-consumer queue. There's message slots. They're generally fixed size. And there's a reader index and a writer index, or a producer index and a consumer index. If they're equal, it's empty. And this is a lockless structure, which is important because atomics are needed for locks, in-memory locks. You can do something over the network, a lot of options. But doing a compare and swap that tells you whether I'm the one who set that flag doesn't happen on CXL. So this is lockless because the reader only mutates the reader index and the writer only mutates the writer index. And so there is no race to update any one thing. And so this kind of thing is doable. And in fact, in the Famfs distribution, there's a program and a library, libpcq and pcq.c, stands for producer consumer queue. It implements this. And it works from one host to another. Now, number one, I don't have cache coherent memory yet. I'm not aware of it being built. Somebody's probably got it in an FPGA now, but I don't have access to that at the moment. And so if you put a message in the queue, you've got a couple issues. Let's say the consumer just read a message, and then he discovers that another message has been put in there. There's a good chance that the CPU preloaded the processor cache past the message that I've actually consumed. So I'm probably going to be looking at stale cache there. I have to be able to detect that. Now, that would be fixed by back and validate. Without back and validate, the way the PCQ example in Famfs works is it uses sequence numbers and checksums on the messages. So if I read a message and it's got the wrong sequence number or a bad checksum or both, then I invalidate the cache and try again. And that works. That's solid. It's not necessarily the killer app for super fast messaging because you do have to do the checksum thing. But it does work. And so I had a slide about memory ordering before. With CXL, atomics go away. But what you've got is CL flush opt and CLWB, which is write back. CL flush opt writes back the line if it's dirty and invalidates it from the cache. CLWB will just write it back if it's dirty. Those are weakly ordered, and barriers wait for any pending ones to complete. So it's an interesting hybrid situation, actually. If I issue a memory barrier on a general purpose CPU with general purpose cached memory that's private, the memory barrier will wait for all. Number one, it tells the compiler, don't reorder anything across this boundary. That's actually a key thing about barriers, is it tells the compiler not to move, because otherwise, bets are off. Compilers are allowed to reorder as much as they want, so long as if you check the value of a variable that was set previously in the code, you see the value, right? And so anything that you can't see, they can reorder. So CL flush, barrier. But in the CXL case, now the barriers are only going to wait for things that you've explicitly CL flushed or CLWB'd. So you do need to do them explicitly if they matter. So if I'm writing it to a producer-consumer queue, I'll write the message to the queue, call either CLB or CL flush, depending whether I want to kick it out of the cache or not. Chances are, in that case, I do want to kick it out of the cache because I'm the producer. I don't need to read that again. And so then I call the write barrier or the store fence, and we're good. But it's barriers in the disaggregated memory. There are some memory accesses that they may not affect. in the shared memory, and that's whatever you didn't flush or force a write back of. Still, you have to do it if you want it to work, so it's actually not that hard to do. And so, yeah, lock avoidance, that's what I recommend people do with this. You know, if we do fine-grained synchronization, however bad it is, I mean, these synchronization things, they just work to the cache. If you do an atomic compare and swap, the cache got updated. It hadn't been written back. That's lazy. You don't know when it's going to be written back unless you call one of the cache flushing instructions. And so, but you don't need to care about that because the cache is authoritative as to the contents of anything that's in cache. But now there's this layer behind the external memory where you may need somebody else to be able to find it. So, okay. So I'm going to talk about what disaggregated memory is going to look like. Today we kind of have static configurations, but soon we'll have DCDs. This is the same slide I had earlier. Decided I wanted to make this point early. There's system RAM. That's not what I'm talking about. There's DAX or Famfs. That's what I am talking about. And so in case anybody doesn't know what DAX is, DAX is memory that Linux has in the system memory map, but isn't using. The way you can get it, you know, on a system with just regular memory, you can mark off some and make it DAX by getting the special purpose memory attribute set for that range. And you can do this kind of thing from the kernel command line. And so, but when there's like a CXL memory device or a little bit down the road when there's disaggregated stuff and the individual devices are discoverable, those will surface as DAX devices. And when you memory map a DAX device, that's just the memory. You know, it brings that, the memory that's associated with that DAX device into your process address space. So a little bit about DCDs. I've got direct attached memory here, and that's just those devices get discovered. Right now, they generally get mapped by the system firmware. And then you either have a dev DAX device or you can use the DAX CTL CLI, which is, that's part of pmem.io. It's been out there for years, to convert it between its available states, which is dev DAX or system RAM. And then with DCDs, you theoretically could have a direct attached DCD, but you wouldn't be able to use the memory until you allocate some. That's a fabric manager command. You could have a multi-headed DCD. MHD is multi-headed device. There's been debate about whether, you know, if CXL doesn't need big fan outs from memory to hosts, then maybe we build multi-headed devices. You can probably get up to maybe 8. And that's probably a little bit lower overhead than going through a switch. But once you're multi-headed, you probably want them to be DCDs because you need to be able to allocate. And when you allocate, you specify shareable or not. If it's not shareable, nobody can ever get access to it. And when it's freed, it's sanitized. If it is shareable, you can, and as a software guy, I wish I paid attention when this was done because it's not software-like, but you issue the same allocate command a second time, but it's a flavor that says, oh, I know this, the tag, oh, these things have UUID tags. So there's this namespace of all the allocations that have been done. So if I've allocated it for host A and it's shareable, I can reference that tag and give access to host B. Also, when I allocated it the first time, I specified whether it should be hardware or software cache coherent. And that depends on devices that support it. Yes, sir? No. No. Offsets and object IDs are your friend. Yes? So it's a property of the allocation that's only available if the memory device supports it. Yes. Now, I guess, I think it's nonsense to allocate a cache coherent object and then try to give it non-cache coherent to another node. In fact, I think I wrote the part that says you can't do that. But, right. There's actually, maybe that's a rat hole I don't want to go in. Does that answer your question, or any follow-up? So I think you wouldn't be able to do, say, a non-cache coherent allocation and then give it to somebody else cache coherent. I think that's just nonsense. And if we set that aside as nonsense, then I think everything else, now you and I could each have access to a chunk of memory and we could do dumb stuff, and that wouldn't work out well for us. But if we did something like, I publish a data set in there, or better yet, I format it as a Famfs file system, dump a bunch of data sets in there, and then you mount it. Now we've got a file that maps to each data set that you and I can both see. And I've got more about this later, but if we make those files writable for you, they are writable for you. And that's a loaded weapon that you need to be careful with. But, and my feeling is that most of the time, the use cases that can be enabled really elegantly are somebody publishes and then a cluster accesses and doesn't mutate in place. And I feel like I've still, let's see if we can pick up the rest of that later. And I'm happy to talk offline too. Okay, so DCDs, they allocate, the allocations have properties, read-write or read-only. One of the things, if you know that your cluster is one writer and everybody else is readers, map it as read-only, and then to the readers, and then the memory device will drop writes. And again, I added that to the spec. Okay, so then, and in a switched environment, you can have really a lot of DCDs, and there's some interestingness there, but I'm going to push it out to another thing. So the tag capacity namespace. So I allocated some memory for host A with tag 0. And tags, think of them as UUIDs. In some of my examples, I use names like foo and bar, but they're UUIDs. They do need to be globally unique. They're generally generated by the device, which needs to use UUID generation discipline to be able to basically guarantee that they're unique. But tag 0 got allocated for host A, and then it got provided to hosts B and C. So now they can see that tag. Which means they each see a DAX device. And actually the naming conventions, how you resolve a tag to a DAX device, that's a thing we're haggling about right now in the Linux development for this. It's not stabilized yet. But we don't have devices that give you tags yet, so that's fine. So then, here's allocating a couple of more allocations, DAX devices, tags, for host A that are not shared. And, oh, by the way, so the size limitations of these, the spec lets them go really ridiculously small in terms of the extent sizes that you can use, but think of it in terms of a gigabyte or more. I suspect nobody's going to build, this is not for your fine-grained allocation, this is for your coarse-grained allocation. And you're going to want to interleave across these, by the way. So then I allocated tag 3 for host B and also gave it to host C. And now I've allocated a couple more non-shared ones. I mean, think of this. This is one DCD, but maybe the next slide. So, but a JBOM is going to have a lot of DCDs. So there's work for the fabric manager to do here. Because, you know, and this is, I don't remember if I've got bullets on a slide about this, but probably I do. When I come to it, I'll say, oh yeah, I talked about that. Oh, okay. 10 minutes left. When we use memory in a regular server, It's always interleaved. We're always constructing the memory map to interleave across all the memory channels. That's a key thing for performance. That doesn't really affect latency, but it does affect throughput. In CXL, what's going to make sense is not allocating one tagged capacity instance, which is necessarily from one DCD. That's one memory device. You're going to want 16, and you want to interleave across them, usually. And so, so the Fabric Manager's got real work to do. All right, so let's get into Famfs. So you could think of Famfs as a memory allocator, where what you get when you allocate memory is a file. It's got some limitations. It's memory, it's not storage. So you probably don't, hey Gary, you probably don't put your only copy of valuable data there. It's generally going to be data you've already got in storage, and probably you moved it into Famfs, copied it into Famfs. There are some major limitations. It's not full POSIX. The particular thing is that files are strictly pre-allocated. So you can copy files into Famfs with the Famfs CLI. It supports wildcards and recursive. And copy is great because you look at the source and you know how big it is. So allocate the right size, move the data in. But one of the ways, actually a fundamental thing about Famfs is that, again, if it's a Famfs instance that lives on one DAX device, they're going to spread onto many DAX devices. But if it lives on one, the master node is the one that ran makefs up here. And the master node is the only node that's allowed to create files. This is a thing that can be mitigated with more complexity. And the way we make this work, the only thing that nodes have to share is ability to read the contents of the memory. And so, in a DAX device that's Famfs, there's a super block at offset 0, just like you would find on a block device. At offset 2 megabytes, but it's in the super block, so if it ever changes, it can change. At offset 2 megabytes, there's a metadata log. The metadata log is append-only. So it's a log-structured file system with an append-only log. So there's a way to extend the log if you needed more. And then the biggest problem that I wanted to avoid early was the risk that there is clients. Let's say if I let you delete files, and I don't currently, but if I let you delete a file, then some nodes could see that file's gone and there's a new file that points to that memory. Nodes that are behind on playing the log still see the old file. And without doing cluster Byzantine general stuff, you can't solve that problem. And so for the MVP version, files are pre-allocated. You can't delete them, you can't append them, you can't truncate them. As long as you don't want to do that stuff, you can do a lot. And a big thing that people latch into their heads when I say that part that I just said is, okay, so only the master can write files and everybody else can read them. It's like, no, actually, mutating the data in a file can be done from any node if you allow it to. So you could do a thing like master creates a set of files, one for me to write, one for you to write, one for you to write, one for you to write, and that's fine. And so there's ways to make this more flexible. One is take the metadata log out of the memory and make it a network service. And you can track who's gotten how far and things like that. Another one there's been some real interest in is having PNFS orchestrate this into the namespace such that, because PNFS can lock you out of files while they're being moved in or out, and can enforce that there is a consistent view. Question, yes? No, it does. It's just memory. So, yeah, and oh yeah, sorry. Can you mmap? Because mmap is usually dealing with files that are on media. I'm going to jump ahead because I got slides on this. So the file system, actually maybe what I do want to do is go here. So what does the file system in the VFS do for you? It maps storage, allocates storage. It does in-memory caching. It does local memory allocation for that caching. And it does memory sharing on a single host. So if you and I both mmap the same file, map shared, you can do it with a cow thing too. But if we both map it map shared, we see the same pages, and they may get paged in. So then there's anonymous mmap, and that's really how malloc gets his arenas. Arenas are what an allocator then allocates from. Arenas are big, allocs are smaller. And so an anonymous mmap there's a file there. It's anonymous because nobody can find the file. But you're using a file for your memory mapping. So then RAMFS, TempFS, HugeTL, BFS, those are just memory allocation and memory sharing because they don't have a backing store. You can have a file system without a backing store. In a sense, FamFS is that because the backing is memory. So then you get to FS stacks. This was originally done for PMEM. And in FS stacks, the file system is providing memory sharing and DAX memory allocation. And that's different because everything to the left of DAX allocation is system RAM. And so, but when you're doing the FS DAX thing, if I mmap a file, it's cache line level access. There's no, so we talk about page faults for data movement, but there's a shit ton of page faults that aren't data movement. I didn't have a TLB, and the page table entry was missing. So you ask the file system, where is it? The file system says, oh, that offset in that file is at this offset on this DAX device. And then page table entry appears, TLB appears, and you keep going, because it is memory. And then, so the missing link was FamFS for multi-host sharing, because XFS runs in FS DAX mode, but it caches metadata. So I can't have the same DAX device visible on two hosts and mount XFS readable, or writable anyway. You can do read-only. It's a little hacky, but we've done it. So FamFS, and the way we solve this is with the log is append only. We don't delete files, we don't truncate, we don't append. And we have a lot of ideas about how to generalize that. But so far, a lot of the feedback is, okay, once we understand those limitations, we can work around them. I can still tell, RocksDB can happily run against files in memory, or files in FamFS. Tell it not to mutate them. Because when it mutates them, I'm getting low on time. If you mutate the files, it's typical that you truncate it to empty and then append till you're done. Okay, can't do that, but you can drop the truncate, like DD. You can DD into these files. You have to say conv equals no trunk. Because otherwise, you probably don't notice, but DD does a truncate on the destination. So anyway, that's basically time. This was another picture. That's a regular file system where it's sparse, but it doesn't have to be sparse. And so anyway, thank you for listening. Any more questions? I'm happy to take offline either emails or corner me. But FamFS is open source. It's working its way towards the kernel. A thing I didn't talk about was that the original, there's 2 implementations of FamFS right now that I'm maintaining, and I very much look forward to cutting that back to 1. There's the original version, which was standalone. That's actually based on RAMFS plus the FS DAX stuff from XFS. But now there's a Fuse version. And the Fuse version was a fairly substantial change to Fuse because this is memory, so we can't be going up to user space and stuff. So the way it works is when you open a Fuse file, Fuse kernel, the FamFS part of it now, retrieves the entire map of the file. And the entire map of the file is cached. So now you're back to, if there's a TLB miss and a page table miss, you've got the whole map in memory in the kernel, and so it's memory speed. Yes, sir? So, you can partition off some of system RAM, especially at boot time. You can reserve some. That's how most of the test automation works. But when you do that, it's inherently not shared, unless you use it to share across VMs and stuff like that. You can do VirtIO. Well, you can do VirtIO PMEM devices for VMs backed by the same file in the hypervisor. And then you can have a cluster of VMs that see shared memory. That's of limited interest because that memory is properly cache coherent because it's actually cached in the hypervisor. Yeah. Follow up or? Listen, thanks everybody. I hope.